So hello guys, I am Sandeep Mandal from Des Engineering, and today's topic of discussion will be uh, analysis of hyperelastic material. I am taking one example to explain that how the behavior of hyperelastic material will conceive or progress in any application. So I am taking an application of trampoline, and I'm fixing it in a fixture and providing a ball, and I'm drop downing the ball. There is a function that if you drop a ball of a heavy steel ball on a trampoline, then there may be a possibility that the behavior of trampoline will be transient, and deformation caused by this will produce a heavy impact on the springs and rigid structure. So this example shows us how the behavior of a hyperelastic material will be in transient condition. So this is the ansys module, and these are the tools. Here transient structural we will be using to analyze. So this is our transient structural. So put it in this way. So hyperelastic material is somewhat like inflatable material, such as vinyl material, nylon material. So these materials are very useful in industrial purposes, such as if you are taking an example of CVT belt, leather belt. These are all an example. It is not a totally hyperelastic material. It is some type of hyperelastic material, because it contains some hyperelasticity property in it, such as if you take a CVT belt, continuously variable transmission belt, and etc., because it can stretch and sustain a thermal stability in it. So focusing in our topic, that is trampoline, in this video I will be showing you how to set up uh, all the assembling structure in ansys. But I produced one model in Creo, that is one rigid structure, one hyperelastic material of 1 mm thickness, and one ball situated over it at a particular distance. I am giving it a gravitational force and dropping down that ball into a hyperelastic material, and then we will be seeing a hyperelasticity or transient behavior of that material. So first, go to engineering material. Here we have to select two types of material. One is hyperelastic material, and then hyperelastic material for that trampoline sheet, and second one is second one is aluminum alloy ball, which you can select any of the material, but in my application I am selecting aluminum ball, so that it contain heavy mass and produce a higher transient behavioral phenomena on material. So by going engineering data source, you will get this tab, engineering data source tab. From here scroll down and select a hyperelastic material. By selecting hyperelastic material, you will get some contents of hyperelastic material here. So in this tab you will get several materials, such as this revilyn material, this elastomer neon, neo hyperelastic material, and neoprene rubber. So you have to select. Here my application is for selecting revilyn material. So click on add. After clicking add, it will be added into your filter or basic basic model, that is on that part we will be indicating static structural or structural steel material. My PC is not responding properly because some files are some files of the softwares are corrupt, but no worry, it will work. After selecting a mone relevant material, and sorry, I previously told you I am selecting a ball of aluminum alloy, but in my PC that engineering data source is not responding properly, so I'm considering the rigid structure as structural steel as a default material, and also the rigid ball is of static structural only because it take less time to explain. So now after ejecting out from engineering data, it's time for geometry selection. So go for geometry and select new design modular geometry. From here we'll be attaching our external geometry file which I created previously in Creo, and it make sure it is in the form of IGS or step file. So here is our design modular. From here we can attach a file, import external geometry file, and this is the which I created this step file. I'm importing this file here, and make sure that no, it is okay. Generate. So this is trampoline structure. So this is will be a rigid fixture, and this is our hyperelastic material, and this ball is dropped here, and after dropping this ball on this hyperelastic material we will be seeing that behavioral changes of this material. It is of thin sheet of 1 mm. This spherical ball is made up of structural steel, and these connections are connected with the help of spring. Now you'll see I've not imported the spring file because in ansys there is a joint function. From there we can connect a animated spring default in the default position, because there is an option of connection joints making. So these are three parts. Now exiting design modular, we have to go for mechanical model. Open that mechanical model first. So you will see the part is refreshed here. So the parts are modeled, so we have to create mesh. So we have to create a different types of structural mesh here because these all are disconnected part. So first we have to create mesh in the hyperelastic material, followed by this ball, and there is no need to connect mesh this surface because these are these are connected with the help of spring. I am only producing a joint here with the help of spring. So let's go for mesh. First go for geometry, select this ball. It is not flexible, it is rigid ball, and by going it is default structural steel. This is hyperelastic material, this is flexible, and go here. You will see that I imported hyperelastic material as mone revilyn, but it is not appearing here. This is because the files are not proper. If I do so, then it will consume very much time. So what you will do is go to edit structural, go to new material, and from that go to engineering data source and select the mone revilyn material. So that okay, I'm selecting I'm doing it in back end of the calculation. So this is our, and this is also rigid fixture. So going for mesh, so go for mesh and generate mesh. So you'll see that mesh only appear in the hyperelastic material because there is no connection between these three geometries. So what I'm doing is building a connection between these two. So go for manual contact region, then here generating a manual contact region. First select this base surface, apply, and now this upper ball, and again this contact is applied. Now base and apply. So you'll see two contact regions, that is red ball and this blue hyperelastic material. Sorry, there is one mistake here because it is not appearing to be blue. So let's go for again. First select ball, then apply, and select this face, and again apply. Now again go for ball and then apply. So our connection get multiplied here. So these are the connection which we made here previously. We have to make another connection regions. So select this ball first, apply. Now this surface, apply. Now again this ball and targeted area, apply. Now this is the, you'll see, and here you'll see that face. So this type of contact region which we have to made, this is necessary constraint for this type of analysis because this ball is dropped into this, and that's why the progression get carried out by this surface. Now so now if you generate mesh, then you will be seeing that the mesh will appear on this ball also. It takes some time. Now we'll see this. So the sizing, if you have a computer with a greater potential or having a good specification, then you can go for sizing and all, but this is the basic requirement for this. This is default meshing condition. Now going for this bonded region, we have to, so selection type, this will be a frictional type of analysis. Frictional coefficient will be 1. Then behavioral phenomena, this should be asymmetric, and go for formulation, augmented Lagrange normal stiffness, manual, and stiffness value will be 0.1. We have to update iterations after each iteration, update a stiffness after each iteration. So, and pinball region will be selecting as radius, and I'm giving it as 7 mm. So you'll see this ball appear here, drop down ball, and that's all. Again go for mesh and generate a mesh. updated. So that's all for connection, and now our mesh is completely ready. It's time for making a connection between these two. So first I will set the analysis setting type of iteration, 3 seconds, auto stepping on, number initial step will be 5000, and minimum number of step will be 500, and maximum times 50,000. So that's all. The analysis will be taken place with these iterations. So you'll see the value here is very high, so it took up to 6 to 7 hours to complete this iteration. 6 to 7 hours. So I'll be skipping the computational time or solving this problem and showing you directly the result, because it takes exactly 7 hours to solve this type of analysis. So now we have to generate connection between these two. It's time for generating so joint creation. Go to contact, insert a joint. So in joint you have to select this part, this section, and go for scope, and now body grounded connection will be there, because this is dropping towards ground. Sorry, this is not to, this is the behavior will be possess towards ground, because the gravitational force will try to push it downward. Now select this, because these end points are the supporting points to this. Apply. Now you'll see this grounding position. So here the connections are made. Now it's time for inserting a joint, inserting a spring. So this is our spring. Now this is very interesting part here. Give it value 100, give it value 100, and so spring length I'm not specifying, because these 2 points are specifying that. So select this internal surfaces, go for scope, and again select these 2 surfaces and again go for scope. So you'll see the spring is automatically joined. So this is only best, sorry, this is very main part to create. If this has any problem, if connection has any problem, then analysis is definitely gone wrong. So make it duplicate. There is 8 hole, so we have to duplicate it 7 times. 4, 5, 6, and then 7. So now go for second, double click, select this internal surfaces, apply to scope, and again select these 2 surfaces and again click on scope. So for third, double click here, select these two internal surfaces, go to scope, and again select these two internal surfaces and again click on scope. Similarly here, select this internal surface, go click on scope, and again select these internal surface and again click on scope. Sorry. So and go here, make sure you have to select a proper surface because the springs are referring the first point which I have previously created, this point. So in similar way you have to create another part and join all the points. So in this way we have to join this with spring, and now it's time for analysis. So click on solution and solve the procedure. So when you are solving this, sorry, this invalid, it's showing invalid time steps. So go to analysis settings, this should be after solving this you'll get the result. So I'm showing you directly result how the behavior will be. So we have done the trampoline analysis, we have set up all the procedure, and this is the force convergence and the force conversion. This is the animation I'm creating here. So let me explain you that first. So in this way the after analysis you can animate the hyperelastic material, how the behavior gonna be, and you'll see the spring response here, and so after generating a report we'll be getting our report is, so in this way we are animating mesh model precisely how our hyperelastic material behave and how the force convergence, and you will see the arrow indicating that upward reaction force on the hyperelastic material when it is forced down. So